Okay, so first, this is the profile of the entire structure that we want to design. Create a surface on it, and then first we derive the first attempt to dissect it into quadrilateral grid. Okay, so this is a quadri mesh, and then use this quadri mesh settings to control the sizes of this dissection. And then we use Kangaroo. Okay, I'll skip this part. Okay, later we can go ahead to do our own process. And oh, this one is not used. Okay, and we define first the anchor. Okay, so I choose the corners, and for each corner I choose 3 vertices to anchor, so that in the form finding process they don't move away. And simulate an anti-gravity, okay, because I want to try to find a curved surface, a curved form, which is more efficient in terms of the structure behavior. And for this purpose, I use 2 object goals object. This one is to simulate the anti-gravity, which is the gravity force going upward. And this one is to simulate as though there is a pressure, inside pressure, that push this mesh outward. And this one is the length goes object. Try to maintain the length of all the edges to be the average of the current size. See this one, this is all the edges, and then calculate the length, and then find the average, and then try to maintain the length of all the edges to be like this. Okay, then we can start. Okay, I should reset. Okay, so now we start initialize with this, and then we try to do the simulation, turn it on. Okay, so it's just like a balloon get blown up, and it derives this shape because all forces are balanced. So I think based on this concept, the surface form might have a more efficient performance, a better performance based on the structure consideration. Okay, and now after a while, the system converged, which means we should turn off the simulation and then derive the result. Okay, and here we can check the mesh. Okay, so this is the mesh that we derive. Okay, but after this deformation, okay, before at the beginning, the edges look very kind of the length of the edges are like very similar, or even they are exactly the same. But after this deformation, they no longer the same size. Okay, but we try to derive this kind of dissection which has the same size for all the lenses, and now we can check it. So this is the mesh, and then we can check it. Let's say find mesh edges, and then we calculate the length and see what happened to the edge length. Okay, so they are different, and we can check the range. Go to mathematics, bound, So they range from 77 centimeters to 87 centimeters. And more likely, everyone has a different length. So it will be very difficult for fabrication. And I think there are, yeah, more than 1,000. Add them together, more than 1,000. Okay. So we try to optimize them, optimize the length of the edges so that it will be easier for fabrication. Then we can go on for the next stage. Okay, so this is the mesh that we have just derived from this Kangaroo process. And this process, oh, I think this is the wrong file. Let me check. I think this one. Yeah. Okay. Okay, this one. Okay, the first step here, I call it form finding. So we start from this, and then we activate Kangaroo, and then we derive the shape. So this process, we call it form finding. And when it is converged, turn it off, and then go on for the next step. And this step, I will call it adjust edge length. So again, we set up the simulation model using Kangaroo and try to equalize the length of all edges to be the average of the edges, okay, and which is 78 centimeters. And then we start the process. Wait a little bit. Okay, converge, then we can turn it off. Okay, and now we can check here. Okay, but I think here like, okay, we have just checked it, right? So, and then we go on. So this is the mesh so far. Okay, and then we go on, but this time, I think they are still of different sizes. Let's check it. Let me see here. These are the lengths, and then we can check the sizes. Okay, we simply take a look. Okay, they are different. Okay, and I think it is impossible to force these edges to be equalized because this is a curved surface. So if you try to do that, then we may end up with a very deformed surface, which we don't want. Okay, so on one hand, we want to keep the shape that we have derived through this simulation using anti-gravity and inflation. And on the other hand, we want to try to adjust the length of the edge so that they can still be categorized into a few different types so that mass production is still feasible. Okay, but we don't know how many classes we can classify. So here we use this k-means clustering. This is an algorithm. I think before I have explained that before. Okay, so we just use it, and this is from Lunchbox machine learning. Okay, and we calculate the length and then set them as the input, and then we have to specify how many clusters our goal. Although we don't know what is the best number for this clustering. I mean, it can be 3, can be 4, can be 5. I mean, of course, if you allow it to classify into more categories, then it will be more possible to get less disagreement. I mean, after the calculation for each cluster, we'll derive the average length of each cluster. So if we divide them into more clusters, then the size of the edge will, of course, more closer to the centroid or the average of every cluster. Okay, but on the other hand, we want to minimize the number of clusters, so we don't need to spend too much for the fabrication. Okay, but this case we really have to do try and error. Okay, and I think in this one, maybe it is quite lucky because I simply try to classify them into 3 clusters, and it turned out to be not bad. Okay, so now when I try to cluster into 3 clusters, and then for each edge will belong to one of the 3 clusters, and then again use Kangaroo goes object to force the length of the edge to be equal to the average of each cluster. So to be equal to one of these 3 lengths. And here we can see that it divides all the edges into 3 groups. One group is closer, the shortest group. The shortest edge are close to 78.3 centimeter. And then the medium size is 80.2 centimeter. And the large size is 82 centimeters. Okay? And this time we try to minimize the discrepancy again using this Kangaroo. Okay, so reset it and then activate them. So now it starts to adjust all the edges and still trying also to maintain the original form. I mean, we can tolerate a little displacement, but hopefully the displacement is still under the tolerance range. Okay, now it is converged. So we stop it, and then we proceed to go on. Okay, so this is the new mesh. And then this one is for checking and also visualization. So this process is called visualization. And we want to check the result, if it is good or bad. So again, for all the edges, we use k-means to classify them. And the same, we classify them into 3 groups. This 25 is for the random seed. Okay. Every time we use a different seed, it will the classification might be different. Okay. So after we classify them, then we compare the length of every edge to the average, to the size, the average size of each group. And then we find out that the largest discrepancy is 1.6 centimeter. Okay? I mean, the size is like 78 centimeter, and some of them, at least one of them, is either smaller or larger than the standard size. I mean, which supposed to be one of these 3, and the discrepancy fall between, this is like 0, I mean 10 to the power of -6, and then to 0.016, which is 1.7 centimeter. And I think in terms of manufacturing, perhaps it is not satisfactory. So we want to set the threshold even further. So here I want to check how many edges has a size which is either too large or too small, but the discrepancy should within 0.01. No, this is not. Okay, 1 centimeter should be between 1 centimeter. Then how many edges pass the result? Oh, sorry. How many edges doesn't pass because the description is larger than 1 centimeter? Okay, it turned out to be okay, only 53. And the edges that pass this threshold is 1013. Okay, and if we somehow make the constraint more strict, for example, if this is a kind of metal, then it requires the precision to be within 1 millimeter. Then, okay, 641 are over this threshold, and 425 are within this threshold. Okay, so it's really depending on our request on the precision. Okay, but anyway, all the edges are divided into 3 clusters. And here, this one, we can show it visually. So you can see that all the edges are divided into 3 different colors: the orange, green, and purple. Okay, and if we want to see what are the edges that does not meet the constraint, these are the ones that has discrepancy more than 1 millimeter, but it will be still smaller than 1.7 centimeter. And these are the edges that perfectly fit the threshold that we set as 1 millimeter. So if we go back to 1 centimeter, then these are the edges that pass this constraint, and these are the edges that doesn't pass the constraint. So maybe for these edges we have to customize, fabricate, but for these edges, then we can go through a more efficient way of fabrication. Okay, but this is only for the edge, which is different from what I just showed you the video. We want to create the block, and then the block make it more difficult to consider an efficient way for fabrication. Okay, so but I think we can start with the equalization of the edges. So now we know that each of these quadrangle, the 4 edges of the quadrangle are either the same size as one of the 3 categories,